Okay, great. So it's nice to be here. Thanks for inviting me. So I had trouble deciding on a title last night when I was putting together these slides. And I think both are reasonable agendas. So it's coming at the same ideas from a different angle, right? So when should we connect vision and language? Low level, mid level, or high level? And I thought I had the answer when I started out a little bit ago, and I'll give you the history there. So it's a little bit of an anecdotal talk. Or you can think of it that I'm no longer convinced that we can do things at the high level. We have to push as far as up from the bottom as we can to connect things at the low and maybe mid levels to connect high level things. And I should thank my students who have done all of this work under sometimes my whip or the DARPA PM's whip, yes. Okay, so indeed, I was a naive, young, junior faculty member, and I thought I had the world figured out when I started out. So this is a figure that was in one of my first proposals I wrote, and it never made its way to a paper because I couldn't put it all together. But right, you take an image. What do you do first? You do some detection, some segmentation, some recognition, some low-level processes that will find all of the things we've been working on in computer vision for maybe 20 years now or more. Okay, you could maybe connect these in a mid-level graphical model where nodes are induced by detected objects and maybe actions if it's a video, and you have various geometric or other relational connections on the arcs of that graph. And this is all guided at the top by some magical probabilistic ontology that we would love that we could have and actually guide this reasoning process. And out of it, you get a beautifully human comprehensible sentence that makes a lot of sense. Many students and attempts later, we did make a lot of progress, frankly, actually. So we have systems that in surveillance settings with fixed cameras, we can do object detection, like find a person or a car or a bus, induce nodes in a graph. It's not a graphical model in the way we think of them. It's instead a tripartite graph, and I'll get into that a little bit more in a little bit. And we can do some action recognition on top of that to output a sentence from a top-down ontology. A person is running left, okay? Or we can do some more interesting things where the persons are manipulating objects while they're doing their actions and get other sentences and put this together in what we called a video on an index card engine. The idea was, right, so you have a lot of video, YouTube, Facebook, whatever. We get so much video all the time. And we would like to be able to perhaps have a prioritized set of rules or events that we care about. And we'd like to turn these into text to facilitate easy searching or easy querying or human-computer interaction in other ways. I want you to see, we did this based on what we called an ontology. I've worked with some philosophers. This is nowhere near an actual ontology. It's just a set of nodes and objects and maybe tools or actions and what they might do. And so any triple through this tripartite graph is outputted as essentially an SVO sentence or a templated sentence. Right? So you can do even more sophisticated things, right? So multiple things might be happening in the video, and we might be able to do our low-level detection, elicit nodes in this, again, tripartite graph or ontology, and output relatively rich descriptions of the video, right? Person 1 and person 2 are picking up boxes. You noted that they exchanged the boxes. We're able to maintain their tracking. If you didn't notice the first time, there's a car that drives by right there, and the system gets it all with sort of state-of-the-art vision, circa 2012, if you will. Okay. But you're all saying, well, these videos are so easy, right? The stationary camera, we can do background subtraction. There's actually jitter in the camera, so we wanted to go to harder videos too. Yes, we agree. Harder videos are valuable. And so here is essentially that same system running on YouTube videos. Right? So this is rock climbing. And one human training data for this is a person's climbing a rock wall. So we went through the rigor of labeling lots of data. We had DPM detectors for rock wall, for persons climbing, upright persons, laying down persons, all these visual phrases that we thought were going to get us really far. And in the end, we were able to output sentences like this based on templates. And we also can do this via retrieval You know, and you sometimes get sensible sentences, but if they're not in part of the training corpus, then you just output garbage. But this is the same domain ontology, right? So we had to manually construct a different ontology for this specific extreme sports domain. This is a small subset of that, and we went through the rigor of that. Okay, but how do we scale this? Or our agenda for scaling this was sort of a multi-level reasoning process or inference process. So we noted that, okay, running DPMs, even sparsely on video, is an expensive process. We cannot do that exhaustively for every video that we might want to describe. So say we want to take all of YouTube, if you will, and index it with sentential descriptions to facilitate easy searching. Certainly we cannot run all tens of thousands of DPMs over every frame of every video. So what we did in this work was we had a low-level process that would queue a set of potential objects that may be in the video. And these queues occurred by very low-level feature matching, so Hog3D, color histograms, and so on. And these were learned in a topic model that shared features over language and over these low-level visual features. And so we could extract these from images and get out this bag of words representation in terms of keywords. And every keyword was connected to a DPM or some connector, or some detector. And then those would be run on the video as a way of sort of doing this low-level queuing. And this would, once we ran these over the video, we did what we called SOS, or sparse, which is sparse object stitching. I think this is what SOS stood for. It was really SOS in terms of like a call for help, because it was like our last saving grace to actually make this work. And the idea here was, so we essentially did shot segmentation by semantics. So as the set of objects that were detected in a group of frames changed over time, that would basically say we're done with this semantic shot. We'll connect that shot to an ontology, output a template, a sentence, and move on to the next one. Okay, and this was our system, and we basically spent a good amount of time trying to scale this. And we ultimately got to this final system, which we call video-to-text.net, which is available in live if you want to try it out. It knows about videos like this, so lots of fast motion, lots of jitter. It's a wild monster truck and so on. It also knows about cooking. It's another application domain in my lab, which I actually won't talk about today. It doesn't really know much about much else, for the obvious reason that if you do it this way, you really need to go through the rigor of training all of these systems, all of these detectors, writing down all these domain ontologies, and so on, and then localizing which ontology you should use. And in the end, we didn't really believe that this was the right way to go. Right? But this is a reasonable description. Right? A person driving a monster truck, performing stunts, is doing something with a large group of sitting people, and it just repeats itself because of that semantic shot segmentation, basically. But there's some interesting nuances there, right? So a person, we never saw, in that video, we never saw a person, right? So we don't actually know that it was being driven by a person or a dog or something like that, right? So this type of system, actually no system I'm going to be able to present is able to overcome that. But anyway, that's an issue. So what are the limitations, right? So the motivation for doing this type of vision, and then you have language, and you connect them at this conceptual level, is obviously scale and compositionality, right? So I can learn about boats once, and then I can think about boats in any context and compose them naturally into these rich descriptions, rich sentences. But there are extreme limitations about actually making that work at scale. First, what happens when the vision fails? Okay, I know this is a vision conference, and this might seem a little blasphemous, but it's just, we do make mistakes in what we do in running our detectors, whether or not these are low-level extraction, like feature points, or mid-level attributes, or high-level objects, or actions. Okay, how do you overcome errors in, even not just in vision, but maybe even language parsing, right? So if you're going to do language parsing separately as well, or speech recognition, and so on. Okay, how do you handle large and broad domains, right? We're working now with cooking videos, trying to understand the sequence of events in recipes. Okay, these are huge, much larger domains than we were looking at in the surveillance setting. How can we handle this at scale? Or multiple concurrent domains, right? The goal in video-to-text.net was really to allow anyone to upload any video and convert it to text and then store that index. There are quite many different domains, such as sporting and cooking and so on, and parties. Okay? And how do you grow the system to new domains automatically? How can you learn those ontologies or those tripartite graphs? There is actually a fair amount of work in AI and NLP on that problem, but it's by no means a solved problem. Maybe more importantly, these are not joint systems, right? So language inference cannot reinforce the visual inference, and vice versa, right? Visual inference cannot reinforce the lingual inference, or the speech inference, or the robot motor control, or whatever the other domain is you're looking to go into. And I think this is one of the core limitations of this approach. It's like sort of going from the low to the high and then connecting it to language in that way. And furthermore, most of the systems that I've seen in this way are unidirectional. They basically are designed to go from an image or a video to text and then do subsequent comparisons such as retrieval or search and so on in that conceptual or text space. And that's separate from the visual space. And we'd like to combine them together, right? So we'd like to take like Kristen's system for relative attributes and say, I want a clown that is more like this one and less like that one without actually having to name those more like and less like and just have those attributes detected naturally. And it's hard to do that with these bottom up or let's say these conventional systems. So I will tell you about two other ways we've begun to do it. One is at the mid-level and one is at the low level. And you can get surprisingly far when you do these, let's call them joint embeddings. And that's what we've been experiencing, and that's the direction our group is going to be going in. Okay, so let's start at the mid-level embedding, and this is a joint embedding of video and language using deep networks. I never thought I would say that in a talk, but so we have a visual system on the left side here, and a language system on the right side here, and we basically take Café and basically compute a visual representation over the frames of the video. We extract the top, not the top layer, like the second to top layer that has, I think, 4096 feature vector space. And ultimately, we get what I would think of like sort of a mid-level representation of the visual space. Okay, there's no contribution in this part. This is just, we just use the system. Okay. Similarly, on the right side, we take, if you will, a conventional language parsing system like the Stanford parser. We take our sentence, we parse it, and then we begin the embedding part. We convert that using word2vec into a vector space so that we can indeed learn some nice joint embedding over these two pieces. And the embedding here, though, is also a compositional embedding. So we'll take every word from the sentence, and we'll actually embed it back into that vector space as the composition of a subject and a verb, or a subject and a verb and an object, or a verb and an object. So we'll kind of learn this compositionality naturally in this embedding. Okay? And what is then done, which you may call the sort of the contribution, I guess, is that we jointly embed this visual representation on this vector space with this language representation on this vector space. So I think there's like 4,000 dimension and maybe 500 dimension with a dense weighting matrix that's learned with backpropagation. And it has weights over both sides of vision and language. Right? So the learning process is reinforcing both sides as well. But also the resulting model can go in both directions. Right? So I can show it an image. It can induce the representation in the joint space and then extract language. Or I can give it language, it can induce the representation in the joint space, and then I can do visual search. Right? So this is the type of two-way inference, or two-way generative modeling that you get when you have a system like this. I don't think it's valuable to go through the mathematics. The paper is at AAAI this year. You can look at it there if you like. And just to show you, however, so the embedding cost is sharing over, this is the language embedding term, this is the visual embedding term, and essentially there's a weight matrix that will link the two of these. And we are essentially minimizing the overall cost over the embedding and a joint reconstruction error. So every sample we get, we're always trying to reconstruct it as best as possible on the visual side and the language side. Okay. And quantitatively, you can see that we are able to outperform. So this is a very biased data set. So this is the Chen YouTube data set. So the prior on subject is 77%, which means that nearly 3/4 of all videos have the person as the primary subject. But we can still have an improvement over, so a standard SVM on visual features, a CRF that sits on top of visual features. These are both, let's say, conventional low-level detection to high-level connection to language and so on. Systems that we implemented using the same detectors, same features and so on, so it's a fair comparison. And CCA is a lower-level embedding that requires joint statistical correlation, which you cannot necessarily expect between the representations of vision and language. Right? So statistical correlation goes out the window here. And in verbs and objects, we get an even larger improvement over these. Just some samples from our systems for some standard videos. This is for a sentence retrieval scenario, so not a language generation scenario. You have reasonable outputs. So like, for example, we find the watermelon as the first thing here. This must be a training sample on a similar video, whereas the statistical correlation system is less able to get this mapping. Okay, on the language generation side, we have quite reasonable outputs for everything on I think this is actually the most common. This is the prior, if I'm not mistaken, for this data set. Person plays a violin. Maybe a person plays a flute or something like that. Otherwise, you get other situations where our system is quite more able to link together the right verb and the object because, again, the language reason is able to reinforce the visual side and vice versa. Okay, so what did we learn from that mid-level embedding? Right, so we can do a joint representation at the mid-level that's able to go in both directions and at the same time outperform one direction or the other direction, right? So we don't necessarily need perfect vision anymore, but language can reinforce vision. Okay, and the rest, I think these will be available, the slides. If not, I'll put them on my website. You can look at the details there. Now what's next? How about a lower level embedding, right? No standard parsing, no deep network to get to parts. What can you do with low-level features to directly connect vision and language? Well, if you want to say low-level, then there's no such thing as language either, right? So we just have audio, right? So just a speech signal. I don't think this will work with the thing here. So training data now. So now we're operating in the tabletop blocks world scenario. Much simpler vision scenario. You may laugh, but it's hard enough, trust me. Okay? Let's see here. I should put the microphone near my... All right, so training data for this system. I hope you can hear this. It's more fun if you hear it. Can you hear that or no? Yeah? Good. All right, so... Yeah, but this is... At some point, this student will be looking for a job, and you guys need to hire him. So, right, so training data, an image of a wooden block on the tabletop, and a audio and audio utterance. Okay? No classes. I mean, there are classes intrinsically, but we're not trying to learn a mapping. This is not a classification problem. This is a strict regression problem where we have two vectors over both spaces. Okay? So we approach this at the low level again as a paired sparse coding problem. Right? So we have an audio vector y that's in some dA dimensional vector space and a visual vector x that's in some dV dimensional vector space. These are feature vectors. We are doing manually feature extraction. So on the vision side, I think it's like an RGB histogram and coefficients of a shape basis space. On the audio side, it's MEL frequency spectrum coefficients, just standard features. One could take some level of a deep network if you wanted to and put them right into here, or use Word2Vec. Nothing different here. Okay, and with these two feature vectors, we have respective sparse basis transforms, right? So U is a basis matrix for the visual representation, V is the basis matrix for the audio representation, and alpha is a sparse vector that's paired or linked across these two basis spaces. So this is not really a joint embedding, it's sort of like a linked embedding, if you will. Okay, and we want to essentially learn the mapping. Y is phi x, and learn the inverse. X is phi inverse y, right? And we can write this down as a combined paired dictionary learning problem. You can actually, this is just the easiest way to understand the mathematics, or to write down to formulate the problem. You can actually pose this as learning a single set of bases and just pull them apart. We optimize this with a standard off-the-shelf sparse coding method. And it's essentially a video-audio interpretation of the Huggles paper, this approach right here. There's really sort of off-the-shelf interpretation of that model. We do extend it later, but this is a relatively straightforward extension of that model, right? So what does this get you now, right? So you can learn a forward mapping, phi, right? So if you're given a audio vector x, right, you have your basis matrix U offline. You want to reconstruct x, or compute alpha, which is kind of like the embedding vector of that sample, by minimizing this distance here, this error here. That will give you alpha. And you can directly map alpha over to audio and reconstruct an audio feature vector, y, directly at the low level, right? So there's no understanding, no semantics are here. But you can still do that reconstruction from vision right to audio. And you can go the other way around, right? So you can speak to the system, get an audio signal, y, reconstruct that y, compute alpha, map that over to the visual space, and get a visual feature vector. Right? And so I don't have a sample here, but we've done the case where we've done both sides. All the results I have here from audio to video, but we've done the case where you can go from video to audio and actually reconstruct a sample, and it's comprehensible. It's actually surprisingly comprehensible, goosebumps comprehensible. Where did language come in, or how can language come in here? Right, so well, the syntax of language is compositional. And so in this work, we exploited the fact that all of our utterances were of the form, descriptive form, adjective, noun, right? So it was always color and then shape, right? So blue rectangle, red rhombus, orange circle, or so on. And so we actually read, there's really no time in this talk to go through the details. I will give some more of the details tomorrow in a talk if you're interested. But we essentially are able to enforce a block diagonal structure over those basis matrices U and V and pull apart those two blocks as a compositional representation. So that means we can learn about, say, blue rectangles and red circles, and we'll implicitly know about blue circles and red rectangles without having to train on those specific classes. Right? So let's go through some results and how this comes to life here. So we have, what's this, like maybe 8 shapes and 4 colors. Visual features I already told you about, but basically a Fourier representation of shape, a mean RGB for the color in a segment, standard audio features, and how does this generalize, right? So this is the paired model without trying to learn the structure over that embedding space, and the compositional model is where we actually enforce the block diagonal structure over those basis matrices, and we're able to exploit it. In these experiments, when we're trying to do generalization now, we've given the training data as every sample in our data set except the utterance that we're trying to model here, except the class of utterances. So it has heard about blue things, it has heard about circles, but it has never learned about blue circles in this situation. And when you have the paired model, you get a representation that can match the color, but not the shape. But if you are able to do the compositional representation, then you're able to also learn the shape and the color. And it looks pretty good, right? So in this case, in the red square case, both get shape but not the color. Perhaps in the Fourier representation, square shape is more interesting than the color one, and so on. And we put this onto a robotic system for the first step toward basically robot Lego building.
Red triangle. Red triangle.
So he's saying red triangle. And then the system does not know where the blocks are. The gamma is off. That's actually a red triangle, not an orange triangle. And it's able to attend right to that red triangle directly at the low level. Okay, again, and this is not a classification problem. We did this right through the sparse coding. Okay, so a summary of the low-level work then, right? So we have a physically and lingually grounded set of percepts that can sort of leverage the compositional nature of the physical world and of language. And we think this is a plausible sort of linked modality representation using sparse coding. that will let us realize systems like the following, right? So can robots follow an utterance such as place an orange rectangle on the top of the blue tower to the right of the green tower, right? So this seemingly simple thing that my 3-year-old can do is extremely difficult. It involves visual perception, right? So we need to have some way of doing segmentation, understanding, and so on. Should we do this at the low level, the mid level, or the high level? It involves understanding of the physical world, right? So some physics models and so on. It requires manipulation. So we need to do the control of the robotic arms to actually make this possible. We need to understand the syntax and so on for linguistic interpretations. And then it also needs to do audio perception. Okay, and my view is that a joint representation of this grounded data from various perceptual sensing control modalities is the right approach for getting toward more natural human-robot and human-machine interaction. I think I'll wrap up and take some questions. But so we began the talk saying that low and mid-level embeddings have the potential to connect high-level things. I've given you 2 examples of that, convincing examples, especially the one with the mid-level embedding where our results are state-of-the-art on this data set. And as far as I know, it's the first work to mutually, let's say, allow for mutually reinforcing the interpretations on both sides. The challenge going forward, though, is how can we handle more complex sentence structures and sort of exploit the structure over both of the domains, and yet still remain at the low and the mid levels. Okay. Well, thank you for listening. I'm happy to take some questions.